So P is contractive if this inequality is satisfied for all distinct xy. So there is a well-known theorem for this. First of all, this example shows that basically every contraction mapping is contractive. So this is the counter example. This example shows that this is a contractive map which is not contraction map. So next one. This is the one of important property of contractive mapping on metric space. This is that if a contraction mapping has a fixed point, then it must be unique. And proof is very simple. If we consider if possible, there are two fixed points of a contractive mapping T. This is contractive mapping, and there are two distinct points, fixed point. Then we apply the contraction condition on these points. So we find that d Tx Ty equals to d xy. Now as T is a fixed point, therefore this is equals to Tx equals to x, and there also y is a fixed point. So this is a contradiction because both are non-zero, because x and y are distinct. So if a contractive mapping has a fixed point, then it must be unique. And there are some facts about the motivation of L-distinct fixed point theorem, because we cannot extend Banach contraction principle directly to contractive mapping, because in contraction condition k to the power n has an important role. Whenever we prove that the sequence of Picard iteration is Cauchy sequence, then it helps us, that is k tends to 0. But in case of contractive mapping, this does not hold. So this is an example. Where metric is complete, and this is an contractive mapping, but there is no fixed point. So in this direction, independently two mathematicians, Nemetsky and L-distinct, both proved an important result, which is called L-distinct fixed point theorem, or Nemetsky L-distinct fixed point theorem, and this is that result. Every contractive mapping on compact metric space has a unique fixed point. Moreover, this fixed point is obtained by the Picard iteration, means that any sequence of Picard iteration converge to this fixed point. So but here is this problem, because we have, this is our contraction mapping, which has a fixed point on complete metric space, and here this is our contractive mapping. And we know that every compact metric space is complete. So this is our compact metric space. So for this mapping, this mapping has a fixed point on complete metric space. and this mapping has a fixed point in this class of metric space, means that compact metric space. So there are many generalization of contractivity condition, but our aim is to focus on those contractivity condition which lies between here, means that between contractive and contraction. Of course, all these covers this also, but they admit a fixed point on where complete metric space. So Picard operator means that if T is a self mapping on a metric space X and it has a fixed point or fixed point set is non-empty, singleton, means that there is a only unique fixed point. Then T is called a Picard operator if for every X in X the sequence of Picard iteration. This sequence is called Picard iteration with initial point at X. This converges to always this fixed point. These operators are called Picard operators in the sense of Russ. So there are so many contractions which lies between in this class 5 contractions, and there are so many results which are Picard operator on complete metric space, and besides this F contraction is also lies between in this class, and Mir killer, which is a well-known contraction, is also lies between this class. So first of all, we discuss phi contraction, which is more natural. Basically, motivation of phi contraction is that if we consider contraction inequality, means that usual contraction condition d tx ty. This is less than equals to k time dxy, and here k lies between 0 to 1. So we know that the range of d is r plus means set of non-negative real numbers. So here we multiplied k with a non-negative number k time t, where t belongs to r plus. So this also belongs to where if k lies between 0 to 1 and t is a non-zero real number basically, then t also non-zero real number. Okay, so we can extend this idea kt, product of these two numbers, by using a map. So if we consider this is equals to phi t, this means that phi operate on an element of r plus, and this goes to r plus. So phi mapping is from 0 to infinity or r plus to 0 to infinity. First thing is that, so we can replace this condition, of course generalize this condition by considering this map. dtx ty less than equals to phi operated on dxy, and one condition is deduced from this contraction constant also. We know that as k is less than 1, this means that kt is less than t, because T is a non-negative real number. Okay. So we deduce this property from here. So motivation of the phi contraction is that we can replace the contraction condition by this map. It is positive, yes. R plus sorry, yes, yes, yes. This is only satisfied for T is positive. Okay. So a mapping from here to here is called control function. Is called control function if it satisfies this inequality for all non-zero T. Okay. And if phi is a control function, then this inequality is called phi contraction. So under this restriction, phi t equals to kt, this reduces to usual contraction condition. So there are another examples. This is an important conclusion. That is, every phi contraction map is contractive. So proof is very easy. If we consider two distinct points x, y in x, then dxy is non-zero, means that this is strictly positive. So we can apply the phi contraction condition here, d tx dy less than equals to phi dxy, and as it is strictly positive, so we use the previous condition of control function, we get dxy. So all classes of phi contractions, whether it was Boyd-Wong type or Matkowski type or another type, they lies between contraction and contractive mapping, means that every phi contraction is contractive. No, different. There are so many theorems depending on phi contraction, but most natural result is this is an example of, this is one of the class of control function where phi is monotonically increasing and this sequence is converges. So automatically using these two conditions we prove that phi is control function, because the proof of corresponding theorem is very easy and we naturally prove this theorem directly. And in Boyd-Wong theorem there are another two conditions because this one, because phi is increasing here, so we can deduce phi is control function. And when we prove that the sequence of Picard iteration is Cauchy, then it is easy to using condition second. But it fails in the context of Boyd-Wong theorem, because Boyd-Wong theorem we prove Cauchy sequence by contradiction method. This is the well-known result of Bianchini-Grandolfi, and here every phi contraction mapping where phi is a strong comparison function defined on a complete metric space has a unique fixed point. Also, this forms a Picard operator. And now we generalize condition second, which is generalized by Matkowski. Instead of convergence of series to 0, here they consider this sequence phi to the power n t. This tends to 0 whenever n tending to infinity. So here, therefore, every comparison function is a control function we can deduce from here. It is easy. So this is one example which is a comparison function but not a strongly comparison function. And Matkowski proved a fixed point theorem under phi contraction for this class. This is the main result of Matkowski. Let XD be a complete metric space if phi is a comparison function such that T is phi contraction. Then T has a unique fixed point. And therefore, this conclusion is directly hold. Every contraction is BG type contraction, and this implies this is a Matkowski contraction, and reverse implication need not be true in view of foregoing example. Okay. Now, instead of monotonicity, because in both theorem we assume that phi is monotonically increasing. If we wish to remove the monotonicity requirement, then we need continuity requirement. So simultaneously of first result, Broder proved such type of result. But in the theorem of Broder, there was an extra condition. So after removing this condition, Boyd-Wong proved an important result on phi contraction. So these are some basic notions: right continuity or upper semi-continuity, and merging both of two types continuity, we find another class of semi-continuity. This is upper semi-continuity and right upper semi-continuity. Now, this theorem is very important because in Matkowski theorem and another theorem, both theorem involve a classical method of proof. In these two theorems, we show that Tnx means that sequence of Picard iteration is Cauchy directly, likewise in the proof of Banach contraction principle. But here this is not possible. So in the proof of Boyd-Wong theorem and another theorem associated with this result, we used Cauchyness by contradiction method. Of course, in that theorem we find that this limit dxn xn plus 1 equals to 0, but it does not imply that xn is Cauchy always. So sometimes some authors called such a sequence asymptotically regular Cauchy sequence, and some another authors Unisi said that this is this is called semi-Cauchy sequence. So here we directly prove that in Boyd-Wong theorem this condition holds. This means that sequence of Picard iteration is semi-Cauchy. And by contradiction method, then we show that Xn is Cauchy. So this is result only two condition on phi in Boyd-Wong theorem. First is phi is control function, and second one is continuity requirement, and this is right upper semi-continuous. Only this condition is enough, and many results becomes consequences of this result, because if we consider natural version, means that phi is a continuous and control function, then automatically deduce from this theorem, Boyd-Wong theorem. And one more theorem is proved by Mukherjee. He considered phi is right continuous. So his theorem is also consequence of this. So there are two directions. This means that there are two directions in phi contraction. One direction, in one direction, phi is assumed to be monotonically increasing, and some another one condition regarding convergence of series or convergence of sequence of iterate of phi. And second direction is continuity requirement, for which this theorem is holding. And these are counter examples, because Matkowski theorem, basically Matkowski theorem is generalization of first theorem, but Matkowski theorem and Boyd-Wong both are independent. So this is one example where phi is not comparison function, but phi is Boyd-Wong type function, means that right upper semi-continuous and control function. And this is example from Jaminsky paper, and this example from Matkowski original paper, where phi is comparison function, but not Boyd-Wong type function. Several authors said that Matkowski theorem is generalization of Boyd-Wong, but it is wrong, because these two examples are available in literature. This is the generalization of another generalization of Banach contraction principle, and motivation of this is that this is our Banach contraction condition. If we take lambda equals to 1 minus k, this means that lambda lies between 0 to 1, and 1 is included here but not 0. So from this we get k equals to 1 minus lambda. So if you put this value is here, then this becomes dtx ty less than equals to d xy minus lambda time dxy. Here, so yes, lambda. No, thank you. So this is again replaced by an appropriate map psi, and this becomes weak contraction, generalizing this idea. So this is your this is our weak contraction. Jaminsky shows many equivalent condition on contraction mapping. So under certain set of plane means x square, subset of x square, means that a domain of matrix. So these two conditions are equivalent, Boyd-Wong and weak phi contraction, or under some additional assumption, this is equivalent to Metkoski contraction. Because we use identity minus psi equals to phi. Identity mapping on R plus minus psi equals to phi, and using the properties of each other, we can connect both these two type contractions. So here lower semi-continuity, idea of lower semi-continuity is used, and these are two conditions only. Basically, in original paper of Rhodes proved this theorem, weak contraction principle. So Rhodes use several other conditions, but later on it is proved that only these two conditions are suffice. So if psi belongs to this class, then the weak contraction defined on complete metric space has a unique fixed point. Lastly, we discuss one of the important of novel class of contraction due to Twardowski, which is called F contraction or tau F contraction, because it is depending on a positive constant tau and a mapping phi from positive real numbers, non-negative set of non-negative set of positive real numbers, 0 plus 0 infinity to 0 infinity. So these are three conditions which are imposed by Twardowski. Later on, many authors discuss all these conditions, and capital F from capital F from 0 infinity to 0 infinity. Here 0 is not included, 0 infinity to 0 infinity. Yes. Oh. Here 0 is not included, likewise Boyd-Wong contraction or Metkoski contraction. Yes, diverge. These three conditions are considered by Twardowski. So later on, Popescu and Stein observed that F2 and F3 can be removed from Twardowski result, and also phi is strictly increasing. This condition can be weakened by phi is increasing. So this is one of the most important generalization of F contraction. So we call this theorem Twardowski-Popescu-Stein theorem. Let XD be a metric space and F is a function, real valued function on, this is real valued function. Real valued function defined on 0 plus, 0 infinity, and it is monotonically increasing only. बस ऐसा। Now this is very old but very weak contraction condition, Mir killer, and this is depend on these two constant parameters, epsilon and delta, and more generalized condition is called CJM contraction, Siric-Matkowski-Jamsky contraction. So all these class are light between contraction and contractive mapping, and main significant to introducing these class is that all these class are Picard operator on complete metric space, not compact metric space, and there are some possible interrelationship between them, which is proved by some recent researcher and some old researchers. Matkowski contraction, Matkowski, and that was first contraction series. Matkowski contraction is CJM contraction, and Boyd-Wong contraction is Mir-Killer contraction, and also CJM Mir-Killer contraction is also CJM contraction, and F contraction is also CJM contraction. Therefore, CJM contraction is a large class which contraction and contractive map, and it has a unique fixed point on complete metric space. So under some additional condition, F becomes Matkowski contraction, and under another some additional condition, F contraction becomes Boyd-Wong contraction. But overall, F contraction is independent from Boyd-Wong and Matkowski. Yes, 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 yes. But additionally, some assumptions. I think F is right continuous. Yes. Thank you, After. So we have a complete meeting space, and we have a whole set of contractions. Okay. So if you take any contraction on a complete space, we have a unique system. Maybe we have a maybe different formula. So this was I would say maybe okay. Yes, yes. There are some many classes. Lo- yes. Look. Yes. Pre-compact metric space. Yes. There are 4 or 5 classes which lies between compact metric space and complete metric space, where this contractive mapping has a unique fixed point, which is discussed by many of researchers.